All right. Now, when we talk about thermoregulation, we're talking about maintaining body temperature. Most of us are generally aware that our body temperature is plus or minus around 37 degrees Celsius. Maybe, maybe about a 35 point, I don't know, 6 or 8 to a 37.8 or so, give or take. Again, these numbers don't matter if you recognize that we want to be a little bit above or below 37 degrees Celsius. So we produce more or less heat depending on the rate of metabolism. That's why we talked about metabolism. So we produce And the homeostasis of body temperature can only be maintained. So that homeostasis of plus or minus 37 degrees Celsius can only be maintained if the rate of heat production is relative to the rate of heat loss. So we maintain homeostasis of temperature when rates of heat loss equal rates of heat gain. So we want to look at mechanisms that give us heat gain and heat loss. So the body heat production comes from the utilization of ATP, right? So when we break down food, we need ATP, and it requires a relatively large amount of ATP. So based on the body at rest versus fasting, when our body's at rest, the base level of metabolic activity is referred to as the basal metabolic rate, BMR. Basal metabolic So that's, again, the sum total of anabolic and catabolic reactions that go on in the body when we're at rest. So metabolism at rest. And in order to maintain that basal metabolic rate at rest, the average individual needs somewhere between 1,200 to 1,800 calories per day. Okay, now that's for at rest. So in smaller individuals, it'll be closer to 1,200. In larger individuals, closer to 1,800 to maintain that basal metabolic rate. Anything you do above and beyond rest is going to require more calories. So exercise increases your metabolic rates by anywhere from 15 to 20 times. Now, that doesn't mean you need 15 to 20 times more calories, because some of that is part of your at-rest metabolism, but you're increasing metabolic rates for periods of time during exercise that require additional food intake. Hormones like thyroid hormones, but like ones we already mentioned, testosterone and estrogen and growth hormone, they're going to increase metabolic demand. The nervous system, especially during fight or flight, increases metabolic demand. Body temperature, like in a fever, would increase metabolic demand. In other words, metabolic rates would be going up under those conditions. So most scenarios that you can think of from a day-to-day perspective require or cause an increase in metabolic rate, which means they're going to require more caloric intake. Now, there are some situations where basal metabolic rates might be decreased, but they're usually under unique circumstances like disease, malnutrition, or in very warm climates. That would slow down your basal metabolic rate. Why would metabolic rate slow down in very warm climates?
So your body doesn't overheat?
Yeah, it's part of the mechanism of maintaining body temperature. You know, if you're already in a warm environment, then you're going to slow down any mechanism you can that would otherwise contribute to body temperature. So it would be part of a mechanism addressing, trying to inhibit mechanisms that would otherwise gain heat, right? So when we look at mechanisms that are responsible for heat loss, one of those is called radiation. So radiation is the transfer it's a transfer of cold to hot or vice versa. Okay, so basically wherever we are at any given time, we're going to be in an environment that's either hotter or colder than our body is. And as a result, there's going to be some transfer between the two environments, the temperature of your skin versus the temperature of your environment. That's a transfer that's going to occur called radiation. So it's sometimes also, another example is, well, never mind. That's what we want to remember as far as that goes. Now, conduction is another mechanism. In conduction, we're going to have a transfer of temperatures. For example, conduction might occur when you see a transfer. We'll just summarize it as transfer of temperature from body to a cold object through contact. So you go to the rink to watch a hockey game, not down at the Air Canada Centre, but at a community rink where the environment inside the rink is cold, and you sit on a bench. And you can tell the minute you sit down on the bench that bench is cold. And maybe if you stay to watch the whole first period or whatever the case might be, the bench starts to warm up. That's conduction. Now, if you're in a really cold environment, you may never feel that bench warms up because the difference in transfer is too great. So you're going to lose body temperature, but it's never really going to warm up that bench because you're outdoors, say in a stadium that's outdoors where the temperature difference is so great. But the concept is going to be the same. There's a transfer from your body in that case to the cold object by contact. If you're lucky, you warm up what you're in contact with and it gets to be a bit more comfortable. Now, convection is another mechanism where we can see heat loss. So we're going to see transfer of heat by either air or water. Okay, so again, it's a type of conduction, except that it's not going to be by contact with a hard object or a fixed object. It's by contact or exposure to air or water. So in this case, the air or the water is cooler than body temperature, and the body is attempting to either warm the air or warm the water, and as a result, is losing that temperature, losing that warmth. So the more movement that's occurring with convection, so wind, for example, or water currents, the more faster that transfer of heat is going to occur. You're going to get much colder in moving water than you would in still water sooner, I mean by that. And the same thing with windy weather versus still weather. The transfer of heat will be faster in moving convection heat loss. Does that make sense? We okay with that?
Yes, sir.
Right. And that's one of the reasons why you see people on a very hot day, you might see people fanning themselves. When you fan yourself, you're creating air current, and that's going to create a quicker transfer. In this case, loss of heat because you're trying to cool yourself off. Of course, the irony behind that is it requires muscle activity to fan yourself. So if you're smart, you get somebody else to do the fanning. They might generate heat, but at least the fanning is going to cool you off. That's what kids are for, if you have kids. Don't tell my kids I said that. And evaporation is another mechanism. So with this is basically when we get conversion of a liquid to a vapor, or a gas, if you like, but a vapor. So basically, this is what happens during sweating, right? And also, you might not think of this necessarily, but when you expire air, that air is moist, and that moisture came from within the body. So it's another way of promoting heat loss in the body, which is an advantage in warm climates where you've seen dogs pant. That's essentially a thermoregulation mechanism for dogs, because dogs can't sweat. But we can sweat. So we sweat liquid up to the surface of our skin, where it evaporates on exposure to the air. And that's that conversion of liquid to vapor. And we can lose a significant amount of liquids this way and cool the body in a significant way this way. So we lose through evaporation, both through exhaled air and through sweat. Now, keep in mind, if you're in an environment or you're exercising and your sweat is dripping and you're coated in excessive amounts of fluid, that is going to be removed much slower than smaller amounts do. So dripping sweat removes very little heat. You're going to actually lose more heat through smaller degrees of sweating. And most of you have probably experienced that at one time or another. In an extremely hot environment where you sweat excessively to the point where your skin is wet, it's very difficult to dissipate that heat. So you sort of suffer in that environment. And part of that occurs because the environmental temperature is very close to the body temperature. And so the fluid doesn't get a chance to be converted from liquid to vapor the same way it would if there was a bigger difference in temperature. So we know that exercise requires ATP utilization, and that will generate heat. We know that if you have a fever, that will generate heat. If we have hyperthyroidism, that's going to generate heat. All of those types of scenarios would require these mechanisms that we've talked about, these four mechanisms that we've talked about, to try to promote some heat loss, right? In the interest of homeostasis, in the interest of trying to keep that temperature somewhere, give or take, around that 37 degrees Celsius or so. So what about heat gain? What happens in order for us to gain heat? Let's look at some heat gaining mechanisms. So with heat gain, one of those mechanisms is to activate the sympathetic nervous system. If we increase the sympathetic nervous system, one of the things that's going to happen is we're going to get vasoconstriction of blood vessels to the skin. If we get vasoconstriction of blood vessels to the skin, we're going to decrease sweating. We're going to decrease temperature, exposure to the surface of the skin. So that's going to decrease loss. Now, the other thing that's going to happen when we increase the sympathetic nervous system is that we're going to stimulate the adrenal gland. And when the sympathetic division of the adrenal gland, or sorry, when the sympathetic division of the autonomic nervous system stimulates the adrenal gland, what are we going to be producing in that adrenal gland?
Cortisol.
Okay, not so much when the sympathetic division stimulates the adrenal
Epinephrine?
gland. Pardon me?
Epinephrine?
Yeah, epinephrine and its very close cousin, norepinephrine. Okay, now, you may recall that in order for the sympathetic nervous system to signal its effectors, in this case, the adrenal gland, the neurotransmitter is going to be what? What's the neurotransmitter that the sympathetic nervous system uses to excite its effectors, the effectors that are going to be responsible for fight or flight? What's the neurotransmitter?
Norepinephrine.
It's, sorry, say that again?
Norepinephrine.
Yeah, well, both. Again, we'll keep them together. We're not going to get too worried about differentiating. There are times when that's important, but not for our purposes. So here's the whole idea here. In the nervous system, this is acting as a neurotransmitter. In the endocrine system, they're acting as hormones, but they're going to target the same receptors. And remember, we said way back when, the nervous system is about being quick but short-lived, and the endocrine system is slower but longer lasting. So together, we're going to get our fight or flight response. And in heat gain, what we're trying to do when we increase the release of epinephrine and norepinephrine from the adrenal gland is we're going to increase metabolic activity in many, many tissues. Think of all those tissues responsible for fight or flight, right? So as a result of that, we're going to increase body temperature. So we overall get an effect of increasing basal metabolic rates. Think of fight or flight. So we increase heart rate, we increase respiratory rates, we increase blood flow to skeletal muscles in the nervous system. All of those things are going to increase basal metabolic activities. So those are mechanisms that we're going to take advantage of. Another mechanism that we're going to take advantage of is that the hypothalamus releases TRH. Anybody remember what TRH stands for?
Thyroid releasing hormone.
Yep. And that's going to target the anterior pituitary gland. And the anterior pituitary gland is going to release TSH. Anybody remember what TSH stands for?
Thyroid stimulating hormone?
Right. So that's going to target the thyroid gland. And the thyroid gland is going to release T3 and T4. And we know that T3 and T4 increase oxygen uptake in almost every cell in the body, which means that we can make more ATP in almost every cell in the body. And that's going to increase basal metabolic rates. So we've increased basal metabolic rates. We've reduced some loss. All of these represent heat gain mechanisms. Does that make sense so far? We good?
Yep.
Yes, sir.
Okay, so we got three mechanisms here. Now, a fourth one that we want to talk about. Let's keep it a little brighter. Okay, and again, this is going to involve the hypothalamus as well. So the hypothalamus also has the ability to respond to thermoreceptors. You might remember, and I didn't mention it because I was going to save it to last, but thermoregulation is the responsibility of the hypothalamus as well. So it makes sense that we're talking about this hypothalamus here. So the hypothalamus responds to thermoreceptors. And if the thermoreceptors are signaling an increase, a decrease in body temperature, then what's going to happen is the hypothalamus can respond to thermoreceptors that are talking about a lowering of body temperature, okay, by signaling the area called the primary motor area for shivering. So very specific. This is an efferent pathway from the hypothalamus as opposed to from the cortex. So we got input from the skin and maybe from the spinal cord that is going to signal that we need to raise body temperature. So in order to do that, the thermoreceptors signal the hypothalamus, and the hypothalamus responds by activating the primary area for shivering, primary motor area for shivering. So this is what's going to happen. Okay, now follow this. Okay, so what we're going to get is we're going to get small skeletal muscle contractions. And those small skeletal muscle contractions in one muscle, okay, the muscle we're following, we would call our agonist. So we're going to get small muscle contractions in the agonist muscle, results in a stretch of the antagonist muscle. Okay, you follow that? If you think about the biceps, if you contract the biceps, causes flexion at the elbow. In order to get flexion at the elbow, the antagonist has to stretch. Does that make sense?
Yep.
Okay. Now, what does a muscle do in response to stretch?
Lengthens.
No, in response to stretch. Think about that spinal cord reflex that we talked about way back when.
Contract.
Yeah, so it's going to cause a reflex contraction of the agonist now. Or sorry, I mean of the antagonist, of that muscle that was stretched. Causes a reflex contraction, which in turn stretches the agonist. You follow me?
Yeah.
Now, if we stretch the agonist, what's the response going to be? It's going to
Another
cause a
reflex.
reflex contraction, which then causes a stretch on the antagonist, which causes a reflex contraction, which then stretches the agonist, which causes a reflex contraction. Contraction, stretch, contraction, stretch, contraction, stretch, shivering. You follow me on this one?
Yeah.
So it's repetitive contraction and relaxation with a stretch reflex in between that's going to create a cycle that requires ATP in every phase. When muscles contract, we need ATP. When they relax, we need ATP. The reflex mechanism in between is going to generate that response. So the stretch on the antagonist results in a contraction from that antagonist. When the antagonist contracts, causes stretch on the original muscle, the one we call the agonist, and it now will respond with a reflex contraction, which then causes the original antagonist to stretch, contract, stretch, contract, stretch, antagonist, agonist, antagonist, agonist, shivering. Cycles of repetitive contractions and relaxations that give us shivering. And as a result of utilizing ATP in both the contraction and relaxation phases, increases body temperature. Does that make sense? We okay with that?
Yes, sir.
Yes.
So shivering is otherwise known because it's being regulated at the hypothalamic level. This is described as being an involuntary somatic motor response. Involuntary somatic motor response. Shivering is otherwise known as an involuntary somatic motor response. It's basically an autonomic response, but on skeletal muscle, right? A subconscious contraction relaxation mechanism that results in an increased ATP utilization, increasing body temperature. So what does this look like if we're going to try to sort of summarize? So we keep in mind that the hypothalamus is our thermoregulatory center. We should be pretty comfortable with that. That's not a big surprise. It regulates an awful lot of autonomic functions. So we talked about how there's an endocrine response. Right? We're pretty comfortable with that pathway. And we can put in our mechanisms here. We had thyroid or thyrotropin releasing hormone, thyroid stimulating hormone. Then we had our T3, T4, targets almost every cell in the body to increase basal metabolic rates, right? Then we can talk about the sympathetic response. Right? And when we had the sympathetic response, we targeted the adrenal glands. And the adrenal glands released epinephrine and norepinephrine. And between the sympathetic system, we together increased the basal metabolic rates but we also decreased, or let's we caused vasoconstriction of the blood vessels to the skin, right? So when we increase basal metabolic rates there, we increase basal metabolic rates there. I'm going to have to move this. Okay, on our previous page, we had these numbered. We said that vasoconstriction, we just had it numbered. So that's one mechanism. This was another mechanism. This was another mechanism. And we also said that we targeted the primary motor area for shivering and we finished on skeletal muscle, and we called that the involuntary somatic motor response. So that increased ATP production, which in turn increased basal metabolic rates. Our basal metabolic rates were increased in these situations. All of those things lead to an increase in temperature, and our original stimulus was a decrease in temperature. So we call that our stimulus then. And we initiated 4 distinct pathways that favors or directs towards heat gain. So we had our vasoconstriction that minimized heat loss. We had activation of fight or flight mechanisms through the sympathetic nervous system. We had an endocrine response, and we had our involuntary somatic motor response. All of those things are going to raise body temperatures, right? So that sort of summarized what we were writing down on that other page there. I don't know how well you can see this picture, but this is another way to sort of look at the homeostasis of body temperature. What this page doesn't show us is it's showing us, let's see what we can see here. Let me get a color that you can see. Heat loss centers in the hypothalamus. We got vasodilation going on here because the temperature is going up on this side. The temperature is going down on this side, down on this side. So we get vasoconstriction in this picture, vasodilation in this picture. Sweat glands were activated in this picture so that we get more evaporation going on under the situation where the temperature is rising. And down here, we're going to get skeletal muscles that are activated. Shivering begins. Okay, so this is just sort of summarizing it in a little more of a visual way. But basically what we're talking about is these mechanisms, these 4 sets of mechanisms. Now, the other thing to be aware of is that especially in infants, we have brown fat, and brown fat is described as being thermogenic. So yellow fat or adipose tissue is not thermogenic. The yellow fat is storing triglycerides, which is a potential source for ATP. But in brown fat, we describe it as being thermogenic because when we break it down to the fatty acids, it's going to be much quicker and much more available to be able to make ATP. So it's going to create a temperature change much quicker. So it's going to increase body temperature. So babies are unable to shiver. Infants are unable to shiver. It takes several years before the shivering mechanism becomes well established as a mechanism that can help to regulate body temperature. So infants and babies, they depend on this thermogenic property of brown fat. Newborn babies have a higher percentage of brown fat than we do as adults. So they depend on this because they haven't yet learned to shiver. So when the neurons in the hypothalamus receive inputs from thermoreceptors that say it's cold, the efferent pathway goes to skeletal muscle for shivering, and it goes to brown fat to break down that brown fat in order to be able to create heat from ATP. So this is a sort of dominates in the very young before we learn to shiver.